example of, for example, so if I take x to be R, and if I take A to be a collection of all subsets of R, x, and I take length L as our usual measure actually, okay, something that we like length is something that takes elements from A and gives you, some length of it. Then, and this is essentially what you call the intuitive notion of length is. So we can talk about length of intervals. It's going to be b minus a. We can talk about, length of open sets. Okay, so it's going to be G is some open set. Then I know that G can be written as, union of such intervals. Okay, AI and BI roughly. Okay. And then intuitively I can say that if you want to compute the length, you can do this at BI minus AI actually. This is one way to do it. And so one of the things that we can, that maybe potentially or intuitively we can do is that, what if I have an arbitrary subset of R actually, which does not necessarily have kind of structure, logical structure on it actually. Could be open, closed, could be anything, could be neither actually. How to compute the length of such sets. So one of the idea that could be that, that if I can put this E into an open set, or maybe there can be many open sets, which contains E or which cover E, then I can define length of E to be the smallest of, lengths of G, so infimum of lengths of G such that
G contain E.
So G E is contained in G, or something like that. Okay, so this could be one of a trick. But the trouble is that we can show, and we're going to show today, that there are some subsets of X. There are some subsets of R which you can't compute the length in this way yet. In other words, this notion of length defined in this manner is not well defined actually. It's not even well defined. Because there are sets for which you can't assign any notion of length. This is what the trouble is. Then how to construct a measure on it actually, and maybe how to construct a measure on an abstract space. If I have, for example, X and A, and how can I construct a measure on such kind of an abstract space? The trick is this, and this is a plan suggested by Caratheodry. What did he said? He said that, if you can somehow, I can't define a measure on A, but let's define something that is called an outer measure. I'm going to define it on A into 0 to plus infinity. So define some outer measure, so whatever that means, which which is obviously not a measure, because if outer measure is a measure, then what's the point of doing all that? Okay, so mu star is an outer measure, and obviously you can show that. Okay, so if the mu star is outer measure, then we will try to do what? We will try to find a suitable subcollection of this, what do you call, algebra, sigma-algebra, whatever collection of subsets of X. Okay, so we'll try to find a suitable collection of subsets of X, a subcollection from here. Okay, maybe let's call it A star or something like that, and restrict this mu star, which is defined on whole set, onto this A star. Okay, and then this restriction becomes a measure.
सर तो स्पेस भी चेंज हो जाएगी ना, मेजर स्पेस ओवरऑल वो अलजेब्रा भी रिस्ट्रिक्ट हो जाएगी.
Yes, yes, yes. So you can't have an arbitrary measure or an arbitrary space. Okay. There will be always things which you can't measure. So what you have to essentially do is that try to construct a suitable set of things from A in such a way that when you restrict your outer measure onto that collection, it becomes a measure. Okay, and hence you have what you want actually. Okay. We want to do this in general, but first of all, we want to do this in the context of R actually. Okay. So we want essentially. So what would be our wish actually? So we want essentially. So imagine when you are doing mathematics, okay, I mean, you are mostly dealing with the Borel measurable set. Okay, you haven't encountered any non-Borel measurable set. Okay. So in other words, you must have a notion of measure which can at least make sense or can measure, the Borel measurable sets. Because if you have this, practically we have a measure on Borel sigma-algebra, which I can later on use in all kind of practical applications actually. So at least we want such kind of a measure, which is not necessarily defined on all subsets of R, but at least must be defined on Borel sigma-algebra. So that will be one of the things. And that abstract measure that we are going to define, and we're going to name it as the Lebesgue measure. Okay. That Lebesgue measure, so if I compute another property, what do you want to expect from that measure actually? That if I compute the Lebesgue measure of this interval, it should give you the same length actually. In other words, that Lebesgue, that notion of restricted measure or Lebesgue measure should extend your notion of length actually. So in other words, it should be in agreement with the notion of
but that should be more than this.
Or length actually. So it shouldn't be a strange thing. So if you want to compute, for example, Lebesgue measure of an interval, it should give you something similar to the length actually, and so on and so forth. So that's what essentially we want to do. Okay. The result that I am going to prove are going to be abstract. Okay, we can in particular apply them in this case, but the results are going to be a bit abstract actually. Okay, they're true in general. So let's do it. So what's the plan? The plan is this. Consider a set and a collection of subsets, and then define an outer measure. And try to find a suitable sub-collection on which this outer measure becomes a measure actually.
सर एक कंफ्यूजन हो रही है जब हमारे पास outer measure आ रही है.
नहीं, outer measure is not a measure. That's what I'm going to define actually. You're going to see that outer measure and measure is not a measure.
But what restriction will be?
Yes.
Same.
So what is the outer measure? Quickly, I defined it last time. So map from the collection of all subsets of X into 0 to plus infinity, such that it has following property. So mu star of empty set is 0, and secondly, it's monotonic in its nature. In other words, if A is a subset of B, or A and B are some subsets of X, then mu star of A should not exceed mu star of B. Can't exceed. And the third property is, which makes it different, is that mu star of, so if I have a collection of any, so it's like a sequence of any subsets of X actually, so it's like a sequence of subsets of X, belongs to 2 to the X, then mu star of countable union of these AIs, the mu star is kind of sub-additive. In other words, the mu star of the union is less than or equal to the sum I equal to 1 to infinity of mu star of AI actually. So if I have such kind of a map, we call such a measure as an outer measure. So in measure you have equality, okay, and here you have sub-additivity actually. Okay, it's not equality. That's what it makes a difference actually. Okay? By a null set, I'm going to mean a subset n from 2 to the x is null if
It is contained.
outer measure of this null set is 0.
Sahi.
Okay. Outer measure of null set is 0. So let's begin with the proposition. Okay. And let's take, so what we essentially want to do, so this is what the definition of the outer measure is, but we want to construct an outer measure and then restrict it on some suitable subset collection of subsets. So here's a proposition. So suppose calligraphic C is some collection of subsets of X. Okay. Such that empty and X both are in C. And suppose you have some vague notion of length for this collection actually. So L is what? It's a map from C
to 0 count plus infinity.
0 to plus infinity. Okay, so you have some notion of length. For example, you have, in case of R, you have this notion of length, which is giving you the lengths of the intervals. Okay, with L of empty set to be 0. Then define anything. So I have a collection of subsets of X. Okay, and some notion of length actually. Okay, that is a map from C to infinity with L of empty equal to 0. Then using this map, okay, question, can I define, let us define for example mu star of some subset from E actually. Okay, or mu star define mu star. I can define mu star from where to where?
2 power x
2 to the x into
0
0 to plus infinity, and define that is. So mu star of E. Keeping mu E is not necessarily in C.
सही है वो outer measure.
Question, how can I define it?
सर L के बराबर अगर E जो है C में है, otherwise इसको कुछ और दे दें.
That's what the intuition says, that okay, if E is in C, naturally this outer measure should give you the same as
L.
But if it is not in E, then what should be the definition? And you can get some hint from there, because we already discussed thing there actually, if you think about it. So when x is r and a is 2 to the x and you have some notion of length, then you can define, for example, length of E or the measure of E to be what?
Infimum.
Okay, the smallest of all lengths which cover E actually.
Cover E, सही है.
So if I want to write a definition, what should be my definition here? Obviously it must be infimum. But infimum of what?
G is length of O mu star of E. Mu star of E.
So first of all, if I have an E, okay, then let's try to find some elements from here which can cover your E actually. So in other words, imagine E is contained in the union of I equal to 1 to infinity's AI's actually, where AI's are
And C.
pairwise disjoint as well.
C maybe.
Okay? Right, pairwise disjoint E. Okay? E is contained in AI where AI are from
C से होने ना दे.
C. Okay? So in other words, you can have lots of collections which can cover your E. Then out of these lots of collection, see that which collection is kind of giving you the smallest value. And that smallest value you can maybe define it to be the measure of E actually. So in other words, I need to take the infimum of what? Sum I equal to 1 to infinity of lengths of AI.
So disjoint भी है.
It's not necessary.
अच्छा.
It's not necessary. It's not necessary for now. Okay? So it's pretty natural definition. Okay, makes sense intuitively. So in other words, you had some notion of length. So using some notion of length, you are extending and you are defining kind of a notion for everything. Okay? Then what we can prove is that mu star is an outer measure. Outer measure. Okay? Mu star is outer measure. Let's do it.
So we are doing it just for C. आप mu
Not
star
for
को
C.
just C पे define किया हुआ है ना ये तो.
Mu star is defined on 2 to the x. So what we are saying, so just think about it. So the motivation comes from, R. Think about it. So in R, if you have some sets actually, you can always find, a collection of open sets which can cover that given set actually. And you have a notion of length. So if you want to say talk about the length of that particular set, then naturally the way should be what? That okay, you say that take that covering and compute their length and sum that up, okay, and then that might give you the length of that particular given set actually. So you are particularly saying, say that, okay, see the collection of subsets of X such that phi and X are there. So if phi and x are there, think about it. Okay, you can ask a question. Is it necessary that we can always have such kind of covering? The answer is yes, because x is there.
Right.
X is there. If x would not be there, then you will be in trouble actually. That is not necessary. But since x is in C, then you can always find out covering for any subsets of x. Are you getting the point? So you had a notion of length, okay, a map, it behaves like length on some collection, and then you are saying that yes, I can use that notion of length and extend it and define a notion of outer measure, which I am going to restrict afterwards to a measure. And you have to keep in view that here I am not talking about the context of x equal to r or a to b to the x. So this is pretty much abstract. So in other words, x could be any set, c could be any collection, and l could be any notion of length actually. Okay, so no restriction. One and two are good exercises for you. There's nothing to prove in there. So think about for yourself. So the only thing in the definition of outer measure is going to be the 3x. Okay? And help me out with the proof. What should I do? The argument should be pretty intuitive actually. Think about it. So what you have to essentially do is that you need to pick a collection of subsets, so countable sequence of subsets from sets from the power set of x, a collection of countable collection of sets of x. Okay. All right. Let A1 equal be a collection from 2 to the x actually. And I want to do what? I want to compute the measure of their union. Question, how can I compute it?
Take the sequence of our parent AI and measure according to it.
Sequence of what? Sequence doing what?
Sequence of cover. They cover the for each AIs.
Good. So the one of the trick could be that try to find, because since x is in C, so try to find a cover for each one of these AIs actually, and from there try to cleverly deduce. So let's think about for AI. So I could be anything. Okay. For AI, where I is an n. So you see that a sequence CI1, CI2 from C, such that what properties should it have?
It should, union should cover.
Okay, so the
Union of CI.
union of maybe j equal to 1 to infinity,
CJ1.
Cij must cover
AI.
your AI.
Sorry.
You have to keep in head that there can be many coverings for AI. It's not just one cover. Okay. Shall I make an assumption? And okay, for a given epsilon, positive, imagine that what we want to do, essentially we want to take the infimum on basically this. So imagine for a given epsilon positive, j equal to, okay, so j equal to 1 to infinity,Cij's can be estimated by mu star of ai plus epsilon by 2 to the I actually.
The measure of Cij.
Can I do that? Measure of ai. And,
On the left hand side.
so in other words, what I'm assuming that the measure of mu star of ai, which is the infimum, okay, is this much away from the given covering actually. This is what I'm assuming now. Okay. So either it's going to be equal or there will be difference. So I'm assuming that okay, this is what the difference is. Okay. And then,
left hand side they measure ano sir unke set ke Cij ke
sorry, yeah, length of it. Yes.
length.
Yes, you should have the length. ठीक है? So you got this. Now, give me the covering for the union of AI actually. So each I can be covered by such kind of sets actually. Then the union can be covered by essentially a double union. The union of I, or maybe j equal to 1 to infinity, and union of I equal to 1 to infinity, and
Cij.
Cij. Pretty much natural. Okay? Maybe I must be first and j must be afterwards. To make it. So it's like taking union on both sides. So just take the union on both. How about mu star of the union of I equal to 1 to infinity ai? Because this is infimum, it must be less than or equal to the sum of the lengths of theseCij's actually. Okay, because this is infimum. So in other words, I can estimate this guy by a double sum. I equal to 1 to infinity and j equal to 1 to infinity,
Measure or length.
length of C.
Yeah.
Okay, because this guy is infimum. Okay. And if this is the case, we are done almost actually. Think about it. And now what I need to do, so I can estimate this thing.
By mu star or epsilon by 2i.
Yes. So you have this, so I can say that this is same as I equal to 1 to infinity mu star ai plus epsilon by
2i.
2 raised to I actually. And this is same as
Epsilon is arbitrary.
I equal to 1 to infinity mu star of ai and I equal to 1 to infinity of this epsilon by 2i, so it's a geometric sum, so you can see that this would be essentially epsilon.
So yeah,
Okay? And if this is the case,
epsilon is arbitrary.
you know epsilon is arbitrary. So since the epsilon is arbitrary,